Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. And today is the day we learn how to evaluate an integral expression. So previously, we've learned how to estimate the area underneath curves, so between curves and the x-axis. Today, we're going to show you how to actually figure out the exact area, again, by evaluating those integral expressions. So first things first, just describe what you think this expression represents in terms of the graph. We've sort of talked about it in previous lessons. So maybe you want to sketch something on the graph or describe it in words, but what does that represent? And notice that this graph, so we'll call this f of x, and this graph is f of x, so there's a relationship there. Okay, so what this integral expression represents is that on the interval from -1 to 6, right, because those are our two limits of integration here, this integral represents the area underneath the curve. And when I say underneath the curve, that just means the area between the curve and the x-axis. So again, this integral right here represents that area, or the answer to that integral would be the amount of area that I've currently shaded in. So let's go ahead and let's talk about how to figure out that area. No more rectangles, no more trapezoids for estimation. We're going to figure out how to do, or how to find the actual area. To do that, we need to know what the first fundamental theorem of calculus is. Up here, that's just what I was talking about. We're going to talk about how to evaluate a definite integral. Definite meaning we know what the interval is. So up above it was like -1 to 6, I think. So the first fundamental theorem of calculus. If a function f is continuous on the closed interval a to b, and capital F is an antiderivative of f on the interval a to b, then the integral from a to b of f of x dx is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. Now, this probably looks super confusing, and you may recognize certain parts of this, right? We've sort of talked about this on the left-hand side, but what in the world is an antiderivative? Well, that's what we're going to focus on for the next portion of this lesson, because before we can actually talk about, how to use this entire equation, we need to understand what the word antiderivative means. So we'll come back to this. But again, we're going to break down some vocab first and get some practice with that. And if you have any other questions about the theorem, feel free to write those down and hopefully I answer them. But if not, feel free to share them in class. Okay, so an antiderivative, let me see if I can fit all of this in here. I can. An antiderivative is essentially working backwards from a derivative. So if I have the derivative, we're essentially thinking, okay, what's the original function? Or if I give you a second derivative, the antiderivative would be the first derivative. So what I would encourage you to do is pause the video, and given the derivatives over here, can you figure out what the original function must have been? Maybe there's more than one answer, maybe there's just one answer. But figure out as many of these as you can, and then you can come back and see if you were correct. Okay, so for the first one, if our derivative is 2x, our original function would be x squared. Now some of you may say, well, there's more than one answer, right? It didn't have to be x squared. Maybe it was x squared plus 1. You're correct. It could have been x squared plus 1. Maybe it was x squared minus 99. Sure, could have been that as well. So multiple answers here, but notice that all of them share the x squared. It's just the constants that are different. We'll talk about that idea later on, why you could have an infinite number of different constants. For the second one, we have 3x plus 5. Well, that means my original function needed to be 3/2 x squared plus 5x, and maybe there was another constant on the end, right? But the 3/2 x squared plus 5x, those are non-negotiables. Those had to be in our original function. For sine of x, well, negative cosine of x. If I take the derivative of negative cosine of x, that's going to give me positive sine of x. And then I could add a constant in if I wanted to. 1 over x. This one, a little tricky. I think we know that the original function must have been the natural log of x. However, it's not just the natural log of x, and here's why. This function right here, the domain of this function is all real numbers except 0. The domain of our derivative has to be, the domain of our derivative cannot be greater than the domain of our original function. So if I just put the natural log of x here, well, this is only good on the interval 0 to infinity, right? So our derivative domain can't include numbers that the original function does not. So what that means is that I need to change the original function to match the domain of the derivative, because the derivative is what I was given. So I know that domain is true. I know that this is the domain of the derivative, which means our original function has to have at least that domain. So what I have to do is I have to make this the natural log of the absolute value of x, right? Because now I know that my natural log function is only valid for positive values. So if I make it the absolute value of x, well, that means I can substitute in any number for x I want except for 0, which is fine because the derivative is not defined for 0. But I could substitute in negative numbers for x, and then I would just get a positive number because I'd be taking the absolute value, which would make the natural log function still be defined. So the antiderivative of 1 over x is the natural log of the absolute value of x, not just of x. My next one, e to the x, this one might be the easiest one on here, right? Because the derivative of e to the x is e to the x. So this one doesn't change. Antiderivative of secant squared of x. Well, secant squared is the derivative of tangent of x. So tangent of x plus a constant. We'll be looking at different techniques for finding antiderivatives. Some of them can get quite complicated, right? I think all of these we could probably have figured out just based on what we know about derivatives, but there'll be some where it's not clear what the original function should have been. So we'll get into more of those rules, but not in this lesson. This lesson will focus on more simple ones. Let's answer this question down here, though. Were there multiple antiderivatives for each of the functions above? Why or why not? Go ahead and answer that, and then join us for a discussion. The answer is yes, right? Because we can add on a constant to any original function, and it's not going to change what the derivative is, right? If I have, let me just give you some examples. If I have x squared plus 1, x squared minus 8, x squared by itself, x squared plus 11, all of those derivatives, right, are equal to 2x. And that's because the derivative of a constant is 0. So you can throw whatever constant you want onto the end of your original function, and the derivative is not going to change because the derivative of that constant would be 0. So when we're taking an antiderivative, we just use a c value, and we call that the constant of integration. That means that we understand that there are multiple antiderivatives, and we're just going to use that c to represent any of the possible constants. So if I find the antiderivative of f of x, the antiderivative would be equal to 3x squared minus 5x plus c. And you could think if you took the derivative of what I have in green, it doesn't matter what that c value is, you would still get 6x minus 5, regardless of what number I chose for c. Okay, down below, there's some of the more common differentiation formulas, as well as the integration formulas on the right. So you can kind of compare those. There's also some rules at the bottom, right? Differentiating when you have a constant on the outside of a function, differentiating when you're adding or subtracting fractions. And the integration formulas for those are similar in that you can pull a constant out, and you could also split up the functions and integrate them separately rather than have to add them together first. But you can take a look at that. We're not going to discuss all of those right now for time's sake. What we are going to do, though, is do a little bit of practice finding some antiderivatives. So first off, though, when we do not have top or bottom limits of integration, we call the integral an indefinite integral. And I'll show you an example of that in a second. An indefinite integral is an antiderivative. Okay, so if I have, let's say, let me do a definite integral first. If I want to find the area from a to b of this function f of x, then the answer to that, right, that would be equal to the definite integral from a to b of f of x dx. Whoops. That is a definite integral because you are given these limits of it. Whoa, what is going on? You are given these limits of integration, a and b. It tells you where to start, it tells you where to finish. An indefinite integral just means that you take those away. So an indefinite integral would be the integral of f of x dx. Indefinite integral. And the differences between the two, right? If I look on the left, the definite integral, the answer to that is going to be an area, right? It's going to be a number. On the right, the answer to an indefinite integral is just going to be what the original function is, or what, if I'm taking the antiderivative of a derivative, that's going to give me the original function. My answer to an indefinite integral is a function, whereas the answer to a definite integral is going to be a number. The relationship here is that if I say find the indefinite integral, that's just like me saying find the antiderivative. If I say find the definite integral, well, then you're going to have to do some evaluating as well. You're still going to have to find the antiderivative, but then you're going to have to evaluate that antiderivative at a and b. And again, we'll talk more about that when we get into the first fundamental theorem of calculus. First, though, let's have you do some quick practice finding antiderivatives. You have, I think there's 6 examples here. Yeah, we're not going to go through all of them. Why don't you pause the video, and then I'm going to put the answers up here so you can work through these, and then you can check to see if you're correct. If you don't understand why you're incorrect, then you can always bring those questions to me during class. So pause the video so you don't see the answers, work through them, and then come check. All right, so go ahead and check your answers. Just make sure when you're doing an indefinite integral, which is the same as finding an antiderivative, you do need to have that plus c on there at the end. Because again, we could put any constant we wanted at the end of that antiderivative, and it would still give us the same derivative when we take the derivative. I don't expect you to be experts at finding antiderivatives yet. I expect some of these to actually have been a little bit difficult for you. So we're going to get some more practice, though. This whole second semester, we're going to be, working with antiderivatives. So the more you practice, the better you'll get at it. This is just kind of your first taste. I do want to end this video by going back to that fundamental theorem of calculus and actually figuring out the area underneath a curve, because I think that'll be the first time we do it, where the function is curved rather than made up of straight segments. So let's go back and reiterate what the fundamental theorem of calculus was. So if I have a continuous function on the interval a to b, then I can evaluate, let's do it here. I can evaluate the integral on the interval a to b of f of x dx by finding the antiderivative of f and evaluating it at b, and then subtracting the antiderivative evaluated at a. So what does that look like here? Well, here's our function f of x, right? Here's our a value, here's our b value. So can you find the antiderivative of f and then evaluate it at b, evaluate it at a, and subtract those values? Pause the video, see if you can do that, and then I'll put the work up here. All right, so the antiderivative of f, actually, we'll just write down what f is first. So the antiderivative is denoted by capital F. So f of x here would be negative 0.3 all over 4 times x to the fourth plus 1/2 x squared, plus 1/2 x squared plus 6x plus c. So maybe you got here, maybe you didn't. I'm going to write the whole thing out again. So this integral that is equal to f of 6 minus f of negative 1. And we know, sorry, when I say f, I should say capital F because we have two different f's here. Now, you may think, almost if I have this c on the end, how am I going to substitute into a function that has a c and an x when I only know what my x value is? Well, if you are subtracting f of 6 minus f of 1, and I am going to write out this whole thing for you, I'm going to write it out once. You won't have to keep doing this. Well, this is what you're going to get. Actually, let me do this. So this is equal to negative 0.3 over 4, substitute in 6 for x, Now I'm substituting in -1 for x. Hoping I can fit it. There we go. You'll notice when I subtract capital F of -1, these c's are going to simplify, right? Because I have a plus c and then I'm subtracting the function, so I'll be subtracting a c. So when you're doing a definite integral, you don't actually need to worry about the constant of integration. You don't need to worry about that c value, because when you do your simplifying, right, when you subtract one from the other, those c's are going to simplify. So when you're doing an indefinite integral, when you're just taking the antiderivative, yes, you should include the c value. When you're evaluating a definite integral, right, a definite integral meaning where you have two limits of integration, you do not need to worry about the c's because they will just simplify out in the end anyway. If you want to write them, you can, but I won't be writing them when we go through problems because it's unnecessary. All right, so I just wanted to show you why it's unnecessary. I'm not just disregarding the c for no reason. It's because it simplifies out every single time. If I simplify all of this, and again, I would encourage you not to punch all of this into your calculator. What I would encourage you to do is punch, now I'm going to get rid of the c because I don't need it anymore. Punch this into y1, right? And then in your calculator, use the alpha trace option. Instead of having to write all of this into your calculator. If that's in y1, you can do y1 of 6 minus y1 of -1, and that'll probably make it so you make fewer errors. I just want to clarify before I put this answer up here, I wrote this incorrectly. Some of you may have been wondering this entire video, or for the last few minutes. This should be -0.03. Same thing down here. Not -0.3. When I was doing my math, I was wondering why my answer wasn't coming out to be correct. And that's why. I had missed a 0 in there. So if we have that antiderivative correct, we end up getting an approximate area of 49.788. If you round, if you truncate, it would be 0.787. So again, that is the area between the function and the x-axis over this interval. Okay, we are going to cut the video off there. We'll have some time to practice the rest. Well, we actually only have one more problem, I guess, down below. So you can work on that if you want. Otherwise, we can go over it in class. But as always, enjoy the rest of your day. We will look forward to seeing you next time.